All right, now let's look at the next one. Okay, so this one will work a little bit different, but we follow the same process. We're going to build a map. So what if we're given the quantity of heat and we need to solve for another variable? So this time we're going to give the amount of energy that we got. We're going to figure out how much of these guys were burnt. So remember, this is our conversion set. Okay, we can say that if we do, so we've got nitrogen and hydrogen gives us, I don't know what this is called, nitrate, ammonia, it's ammonia. All right, so if we take 1 mole of nitrogen, we're going to release 92.4 kilojoules of energy. If we do 3 moles of hydrogen, we're going to release 92.4 kilojoules of energy. If we end up with 2 moles of ammonia, we're going to get 92.4 kilojoules of energy. Right? So this one we're going to be given the amount of energy that we got from a reaction. We're going to figure out how much of these would have been burnt. Would have been involved in the reaction. Okay, so right here, I get 1 billion kilojoules of energy. How many moles of nitrogen reacted? So this is what I know. I know 1 billion kilojoules. So what I know, I'm going to do my map. I know my delta H. From my delta H, I need to figure out the moles of nitrogen gas. Okay. So I know my delta H is 1 billion, 1.00 times 10 to the 9 kilojoules. And I don't know how many moles of N2 that would be. So we set up our conversion. Ready? I write it this way. I always write my unknown on top and my known underneath. So how many moles of N2 would have been used to produce negative 1.00 times 10 to the 9 kilojoules? So that's from my question. How many moles would it take to produce that much energy? And it's negative because our delta H is negative. If, this is now my conversion, if 1 mole of N2 being used will get me negative 92.4 kilojoules of energy. Now I just cross multiply. 1 billion times 1 divided by 92.4. And I do 1 billion times 1 is still 1 billion divided by 92.4. It's a stupid big number. 1.08 times 10 to the power of 7. And that would be moles of N2. Right, that's a big number. And this should make sense to you, right? If 1 mole of N2 gets me like around 100 kilojoules of energy, I'm going to need a lot of moles of N2 to get to 1 billion kilojoules of energy. Okay, so make your map, do the conversion. All right, so let's look at the next one. How many moles of ammonia are produced when 1.5 times 10 to the 6 kilojoules are released? Okay, so we're going to make our map. What do we know from the question? We know our energy released. From that, we're going to go to moles of NH3. So we've got 1.5 times 10 to the 6. And we don't know how many moles of NH3 we're going to produce. So we write it up. How many moles of NH3 do I need to produce 1.5 times 10 to the 6 kilojoules of energy? You write that down. How many moles of NH3 do I need to produce 1.5 times 10 to the 6 kilojoules of energy. If 2 moles of ammonia are produced when negative 92, this should be negative down here, negative 92.4 kilojoules of energy are released. So how many moles of NH3, if this much energy is released, the negative means released, if 2 moles of NH3 are produced for every 92.4 kilojoules released. The math is the same. I take this times it by 2 divided by 92.4. Now, I don't know how to use do the powers of 10 stuff on my calculator. So I'm going to just change this into what? 150,000? No, 1.5 million. Yep. 1, 2, 3, 4, 5, 6. Yeah, 1.5 million. And it's negative. Times it by 2 equals 3 million. Negative divided by 92.4. That's negative, so we get positive 32,468 rounded. So our question mark is 32,468 moles. That's the answer. So how many moles of ammonia are produced when that much energy is released? Well, if we release that much energy, we should get that for an answer. All right, so let's keep going. We are going to use the same equation. So I'm going to copy it down to this page. 1N2 plus 3H2 gives us 2NH3, NH3, and our delta H is equal to negative 92.4 kilojoules of energy. All right, so our next question. How many liters of hydrogen are used up with the total release of 1, 2, 3, 4, 5, 6 kilojoules? Okay, so let's build a map. So what we know is the amount of energy. So we're going to start with the amount of energy produced. 1, 2, 3, 4, 5, 6 kilojoules. Then from that we can go to the moles of hydrogen. Then once we know the moles of hydrogen, then we can figure out the liters of hydrogen using this conversion. 22.4 liters of anything at standard temperature and pressure is equal to 1 mole of it. So that's an important conversion for gases to moles. All right, so first thing, we need to go from here to here. We can do that in red. So we're figuring out the moles. So I do it right. How many moles of H2 will I use to produce 123,456 kilojoules? If, right, 3 moles of H2 produce negative 92.4 kilojoules of energy. So I do my cross multiplication. 1, 2, 3, 4, 5, 6 times 3 equals 370,368 divided by, oh, this should be negative as well, just so our moles are always positive. Divide that by 92.4, that's negative, and we get 4,008.3 moles. So this much energy was produced if we have 4,008.3 moles of hydrogen gas. Now, we leave the exact number in your calculator, 4008.31168831117. Now we're going to do our second conversion. Now that we know how many moles of hydrogen gas we have to figure out how many liters there are. So write this guy's the question mark now. So I write it like this. How many liters of H2 will I get from 4,008.3 moles of H2 if there are 22.4 liters of H2 in every 1 mole? I do 4,008.3 times 22.4. So I just have to times it by 22.4 on my calculator. 89,786. 89,786 liters. Okay, so I did 2 conversions there. I knew the energy in my question. Then I used the energy related to the number of moles from my chemical equation to figure out how many moles it would take to produce that energy. Then I went from my moles of hydrogen gas to the number of liters using this conversion here. All right, last one. This one is kind of crazy. What mass of ammonia is needed to completely react and release 654,321 kilojoules? Okay, let's build our chart. Let's build our map up at the top. So we start with our energy, 654,321 kilojoules. From that, we can get to our moles of NH3. That's the ammonia. Then from our moles of NH3, then we can go to our grams of NH3. We do this using the molar mass. Okay, so we are going to have to figure out the molar mass of NH3 in a bit. But first, we do this first step. Okay, we're trying to figure out moles. So I write it down. How many moles of NH3 will I get from producing 654,321 kilojoules of energy? It's negative. If, right, I use this guy up here, I get 2 moles of NH3 when I react that much. Oh, I got to put 2 on top. 2 moles, and it's positive, for negative 92.4 kilojoules. Right? Those are related. If I get 2 moles of NH3, 2 moles of ammonium, I'm going to release that much gas, that much energy, sorry. Then I just solve this. 654,321. 654,321. I push that in the wrong calculator, times it by 2, divided by 92.4. 14,162.8. 14,162.8 moles. That's a lot of moles, right? It takes 2 moles to produce that little bit of energy, about 100 kilojoules. So it's going to take a lot of moles to produce that amount of energy. So now we know our moles. Now it's nice to leave that number in your calculator. But now we have to go from moles to mass, to grams. We do that by doing the molar mass. And you should get good at figuring out molar masses because you're going to be doing a lot. So I'm going to just write over here molar mass of NH3. Well, let's go to our thing. N is 14.007. And H is 1.008. And we times that guy by 3. So 1.008 times 3 is 3.024. 3.024 plus 14.007 is 17.031 grams per 1 mole. NH3. Okay, so that's the molar mass. You did them last year. You guys found them easy, I think. So now we're going to come here. We're going to do the last conversion. We don't know how many grams of NH3 there are. So we put that on top. How many grams of NH3 will there be in 14162.8 moles if there are 17.031 grams in 1 mole? So we take that number, and I managed to leave this in my calculator because I did my molar mass in my head, and I just multiply it by 17.031. 241,206 grams. 241,206.5 grams. So if we release that amount of energy, we should have produced that many grams of ammonia, or about 241.2 kilograms of ammonia. So building this map out is important. All right, so we'll go on to the last example in a bit.